couple of Chapter 2 problems now to take a look at here. In this chapter, there's a lot of different components to it, and one of them is the isotopes. And I wanted to go through one problem and give hints on another. And they are problems 2.9, and it's 9.5, and 2.96. Okay, so we're going to take a look at these for a moment, and as always, we're going to first take a quick glance at the problem. So here is problem 95 in Chapter 2. Now, this one is a classic calculation of atomic weight using the weighted averages, the fact that all the isotopes are not created equally. Some are rare, some are fairly common. This one involves lead, and it has 4 different isotopes involved here. So remember the basics of the weighted average here for a moment. We simply take the abundance in decimal form, DECIMAL, in decimal form. They'll usually tell us it's 20% lead 206 or something like that. And so we just move that to 0.2. Okay, move the decimal point over 2 places. We take that and we multiply by the exact mass. And we do this for all the different isotopes. And I don't get to use these symbols very often, and it's so much fun to draw. There it is. Oh, what fun it is to write that. Sum for all the isotopes, they're simply their abundance in decimal form times their exact mass. So, looking at the data in problem 95 for a moment, they give us information about 4 isotopes of lead. What they tell us is that the isotopes are, and glancing over for a moment, lead 204. What I've done is just simply taken its exact mass, the 203.9382 that they handed us in the problem, round that to 204. And then the other 3 isotopes they give us are lead 206, 207, and 208, with the exact masses of 205, 0.9, 0.97444, 206, 0.97587, and 207.97663. Okay, so here's all 4 of the isotopes with their mass number names here, the exact masses, and then of course the percentages. And they tell us this one is 1.4% abundant. So not a lot of that one. I don't even know why there's no lead 205. I don't know. It just doesn't seem to be any. 24.1% for the lead 206. 22.1% for the lead 207. And then finally, 52.4% of lead 208. Now, if you take these numbers and add them up, they will add to 100%. These are the 4 naturally occurring isotopes of lead. And so to solve this problem, which is essentially calculate the atomic weight of lead like you would see it on the periodic table, and certainly you can just look at the periodic table and see the number there. It's, you're going to see lead and its value of its atomic weight written right under the symbol. Okay, but this is the origins of that, and it's important to know that, and important to realize that all the percentages, if this is a complete list, is going to add up to 100%, and in this case it does. So what we do is we set up the calculation, and we take our percentage, put it in decimal form, 0.14. Remember, when I say decimal form, 1.4% is just simply saying 1.4 divided by 100. And if you did that little thing, 0.014. In the net effect, it's just to simply move the decimal point over 2 places. And I just inserted the 0 to make sure I had a place in there. Times its exact mass. 203.9382 plus 0.24 205.97441 times 205.97444 plus, it's just nothing more fun than watching somebody write numbers on a whiteboard, 0.221 times 206.97587. Plus 0.524 times 207.97663. Now, clearly, I have some quality time with my calculator coming up, and so in order to fill the time, why don't you look at these pictures of puppies while I get this thing calculated. I came out with 207.21688, which, if you look at the periodic table, under lead, you should see 207.2. Okay? And there is the atomic weight of lead. So here's this basic calculation, which is a relatively simple one to handle. Now I want to take a look at the related question, question 96, which is similar to this one, but it has one curveball tossed in there. So what I want to do is clear myself a little bit of space here on the board and then talk about that particular problem for a moment. So here we go. There. Now, this problem 96, which is closely related, involves the element gallium, Ga, and it is element 31 on the periodic table. So it has atomic number 31. Part A just simply tells you about the two isotopes of gallium and asks you for the number of protons and the number of neutrons written out, which that one's a fairly trivial one, so we'll do that one real quick. You are told that gallium comes in two isotopes, gallium-69 and gallium-71. Okay? There are the two isotopes of gallium, and with the mass numbers written in the upper left position. And then, of course, the atomic number, the number of protons, is sometimes written there, so I'll put those in. Of course, that means that there are 31 protons in the nuclei of both of these. If you're gallium, you've got 31 protons. There is no doubt about that. Up here, the mass numbers, of course, are simply protons plus neutrons. So if you subtract the two, you come up with the number of neutrons. And for this one, 38 neutrons, 69 minus 31 is 38. For this one, 40 neutrons. Okay? And so there it is. So that's part A. Write the symbols with all the little mass numbers and atomic numbers in place and tell us the number of protons and number of neutrons in each nucleus of these things. So there that is. That one's pretty easy. Part B asks you to figure out the percent abundances. And they come right out and give you the exact atomic weight. You can write that off the periodic table. For this particular question, they're after what is the percent abundance of gallium-69 and what is the percent abundance of gallium-71 given the exact masses and given the overall atomic weight of gallium. So, taking that one into account for a moment. For the gallium-69, we're given its exact mass, 68.926. For the gallium-71, we're given its exact mass at 70.925. And we are told that overall, the average for this thing, when we look at it on the periodic table, is going to be 69.72. Remember, that number is the answer to this calculation. The abundance in decimal form times the exact mass. Add those up for each of the isotopes. That gets you the value that sits on the periodic table. This particular question gives you the answer and gives you the exact masses and asks you for the abundances in decimal form. In other words, this particular problem, knowing kind of where we want to go with it, is simply this. Let X, okay, be the percent abundance for gallium-69, Y, the percent abundance for gallium-71, okay, and these are the percent abundances, And we're essentially told whatever x is times 68.926 plus whatever y is times 70.925 must add up to 69.72. There is the weighted average calculation, this time with the more uncommon unknowns of the percent abundances. Most students get to this point and they will look at it and go, oh my, I have two unknowns and only one equation. And some vague memory of past experience says that ain't good, that there's going to be an issue here. And in fact, there is. This one stumbles a lot of folks. And so I'm going to give you one hint. As soon as you see it, most everybody will go, oh, of course, and off you go, because this really is not that difficult a problem. And the hint is simply this. Remember what we said about percent abundances. If these are all the isotopes, they add up to 100%. In other words, x and y here are not separate independent variables. As remember, whatever x is in its percent form and whatever y is in its percent form add up to 100. Or in decimal form, x and y add up to 1. Okay? And thus I can say, well, x therefore is 1 minus y. And oh my, look at this. I have something for x. If I just took this x and wrote 1 minus y, and make sure that really looks like a pretty y. Not a very pretty y, but anyway. Y times 68.926 plus the original y, 70.925 equals 69.72. Oh my, there is an equation with only one unknown in it. Oh yeah, it's kind of a tedious algebra, but there's how you're going to get the answer. So, remember your isotopes, go forth, calculate, figure out what y is here, and see you later.